Okay.
Yeah.
So the next talk is given by Institute Professor in Taiwan University, Professor Guang, and I believe he will also give us new results. Okay, so let's welcome.
First of all, I'd like to thank Director Chu and Vice Director Guang. So actually, it's my great pleasure and honor to speak here. As you heard yesterday, NCTS was established in 1997. I joined the NTU Physics Department in 1998. So ever since I joined the physics department, I've always been participating and sometimes organizing activity. And I'm happy to see when I, first participate in the activity, the community actually quite small. And in the past 19 years, we grow quite big now. In particular, first principle computational material community. So I remember at that time when Professor Lee was director, he organized 5 core programs, and computational material research is one of them. Okay, so today I think it's fitting that I tell you what can we learn, in condensed matter and material physics from first principle calculation. Okay. So now about 1.5 years ago or 2 years ago, our department chairman, circulated this paper, and many people got quite excited. So basically, from the title, you should get excited if you are physicists. Okay. So let me tell you what it is. It basically shows you that you inject this sulfur dihydride into gas into this diamond MBO, and then you cool it down, become liquid. And then you apply pressure and become solid, and eventually become metal. And then if you increase pressure further, and then it becomes superconductor. Okay, as you increase pressure further, and eventually superconducting temperature can reach 200. Okay, so and this has been confirmed by Meissner effect. And so then. Professor Wu is here. He's the discoverer of cuprate, and this temperature is actually higher than the record high temperature of cuprate. Okay.
Problem is the magnetization.
I must be a mathematician. This is, yeah. Okay, this is just a set to the stage for my talk. Okay, so now if you read carefully, you'll find that the statement. We select this material because it's relatively easy to handle. More importantly, is to predict the transform from a metal to superconductor at a low temperature. Okay, reference 14. Now, what's the reference 14? Reference 14 is actually an initial calculation paper. Okay, published in this not a highly paid journal. It's called Journal Chemistry Physics. Okay, so it basically shows that if you apply pressure under 90 gigapascal, crystal structure and band structure is metal, and if you increase pressure further, you transform to another ortholombic, and the density of state at the formula will increase. And then they further calculate superconducting transition temperature based on electron-photon coupling, and you can see that the pressure increases. Okay, so now this basically suggests that nowadays first principle calculation is really become sometimes predictive and a powerful tool in condensed matter research. Okay, such as searching for new material as high CV super, and also I should mention, steel and other people producing a lot of topological material and waiting for experimental people to synthesize. Okay.
But the first principle does not predict short time.
Yes, this print is directed based on electron photon coupling.
Yeah. So it assumes certain.
Yeah, of course. We cannot do everything. Yeah. Okay, but this is already exciting to me anyway.
The mortality is still not very clear.
No, I think this to me is clear, but to experiment it like NK. But okay, I should not get into debate on it. I focus on what I'm going to say in next. Okay. So basically, this is just want to Okay, so let's come back to my plan of my talk. Basically, first I will tell you what's the first principle calculation and give two examples to illustrate the important role first principle can play in condensed matter research. Okay, then I will show you some examples that we did recently. In particular, we developed this. Okay, then first I show you the spin Hall effect in solid and concept and application. Well, actually, Professor Ko already showed you a lot, so I will be really brief on that. And then, since this theoretical talk, so I basically present quickly the beautiful formulation of calculating intrinsic or intrinsic Hall effect, and then I show you the largest intrinsic spin Hall conductivity we discovered theoretically in this method. Okay, and then in the third part, I will tell you that from the first principle calculation, we propose multi-orbital condor effect in ion doped gold, which is actually condor effect is a classical problem in condensed matter physics, and then we relate this condor effect into gigantic spin Hall effect observed by experimental people. And finally, show you the very recent work that by performing ab initio calculation, we discover an exotic quantum enormous Hall effect, which is called quantum topological Hall effect in this layered oxide. So, what's the first principle? Maybe it would be easier to illustrate by this cartoon. Basically, if you know a compound with element name, and then you can type in atomic number and then key into the computer, and then you let the computer run, and eventually you will say, find is a metal, semiconductor, is magnetic or not. Okay. Now the key ingredient for this that of course we need to have a theory which is based on quantum mechanics, basically by solving Schrödinger equation. And in this calculation, in principle, without any empirical parameter fitted to the experiment. Okay, so that's the first principle calculation. Now is a good time to do this kind of research because we have a very fast computer and the algorithms are also mature, and importantly, we have quantum mechanics theory. So it becomes a very important tool in understanding very complicated phenomena in condensed matter system. Nowadays, as I showed you before, can search or even design new material with the desired problem. Okay, now this is the example I'm going to illustrate that say silicon, for example, if we it's FCC structure and diamond structure, if you cut along 111, you make a surface. If nothing happens, then you see surface like that. Okay. Now, of course, your surface will reconstruct, and nowadays we know it's become so complicated. But during the process, to understand atomic structure, this kind of complex atomic structure, actually, I think ab initio calculation play quite an important role. For example, they can determine the relative energy among several possible surface structure, and then compare, and then also determine very precisely the atomic bond length and so on. And more importantly, they can predict STM image and compare with the experiment. Okay, so that's basically tell you that ab initio calculation can help you to understand such a complicated surface reconstruction. Okay, now maybe I tell you another example which is more related to our work. And you know that the oxide has been a very interesting material in the past 2 or 3 decades. Okay, now because we have superconductivity and later on colossal magnetoresistance and other phenomena like charge orbital ordering. Okay, people believe that many of these phenomena like superconductivity and colossal magnetism are related to charge orbital ordering. Now, charge ordering basically at below certain temperature, all these itinerant electrons suddenly localize to form such like a stripe and also in the meantime can be occupy 13 orbitals. So that's orbital charge orbital ordering. But however, the first charge ordering model was already proposed in 1941 by Verby. Okay, but that model was controversial until 2004, or around that time. Now, this was proposed in this magnetite, which actually many of you must be familiar with, used to make a compass. Okay, so it has been around more than maybe 2000. Okay, but it is still a highly interesting material for research. Now, basically, in 1939, Verby found that if you cool the material down, the conductivity resistivity suddenly jumped, okay, from metallic-like to insulating-like. Okay. Now, further analysis found that it has this kind of FCC crystal structure, and ion has two kinds of valence, 3 plus, and then another one, 3 plus, and 2 plus, on 2 different sublattices. Okay. Now the interesting one is that this is not very active magnetically, but this one, because it's add up to 2.5 mixed valence state. Okay. So then, because of that mixed valence, so Verby proposed in 1941 that at below 120 Kelvin, 3 plus will order this way, and 2 plus order this way. So this is the first model for charge ordering model. Okay, and however, soon that the model was disproved by X-ray diffraction because the symmetry is not correct. Okay, and that's become at that time, I guess, becoming hot topic, like Nobel laureate P.W. Anderson, and also look at it and propose Anderson criteria. Neville Mott also proposed Wegener crystal and Wegener glass transformation. Okay. Now, Neville Mott even organized an international workshop completely devoted to Verby transmission. That's quite unusual, okay? But then this 1980 and 2002, and there's a review paper in Journal of Physics Condensed Matter saying that okay, many experimental aspects are clear now, but the fundamental issue remains. Okay. Now, in the same journal 2 years later, 2004. And another review article by a different group saying that in this review we refute all the arguments advanced by the author. The same journal, okay? So that's why I said this problem will remain for a long time, okay? Now, why I say that, that's where we come in. Okay. Basically, in 2002, this Cambridge group called active field published a neutron scattering measurement and determine the atomic structure. Okay, so what we do then, we just perform LD plus U calculation and discover that if we use high temperature cubic structure, it's a metal. Okay, if we use this new structure, you find it becomes a semiconductor. Okay, this is a gap, and then ion in this state, this so-called T2G band half metallic, and this band split off, and then we plot this charge density in the real space, and this reveal. But not only this explains the metal insulation, but also this is very important. For the first time, we found that in this material, this conducting electron actually below that temperature become orbital order. You can see that this can be transformed into dxy, dyz, and dxz. Okay, so this really we discover ion T2G orbital order, and that explains the Verby's original, because the orbital ordering associated with this orbital ordering, you can also see charge ordering. Okay, so that's, and then we not only propose that, but we also predict that if you do X-ray absorption measurement at the K edge, and you'll be able to see charge ordering on the oxygen side. Okay, and then our friend Guang and they performed inelastic X-ray scattering, indeed confirm our prediction. And one of the curve is my configuration, and the other is their inelastic X-ray scattering. So we think at this time we solve a very long-standing problem in quantum method. It's basically the classical charge orbital ordering predicted by Worley is actually ion T2G charge orbital ordering course. Okay, so that's one example. Now move back on to our more recent work, which I'm going to talk about, is the spin Hall effect in solid. Now let me, well, some of the things Professor Guang already said. Let me begin with the ordinary Hall effect. Basically, if you are doing an IV curve measurement, for ordinary conductor, if you apply perpendicular magnetic field, you also find transverse Hall voltage, and this is known as Hall voltage, and this effect is called Hall effect. Okay. Now, characteristic of this Hall effect is that the transverse resistivity is a linear function of magnetic field. Okay. And the longitudinal one changes slightly, and that's called magnetoresistance. Okay. And then 2 years later, Erwin Hall also found that instead of non-magnetic conductor, if you have now a magnetic conductor, and you have additional Hall effect, which is proportional not only to magnetic field but also to magnetization. Okay? But at that time, I guess he could not understand it. That's why it's called enormous Hall effect. Okay. Now, of course, we know that at least polar theory, this is due to spin-orbit coupling and, well, relative spin-orbit coupling and magnetization in the same time. Basically, you can see that with spin-orbit coupling, electron going through, when electron move, okay, in this solid, spin-up electron will be scattered into one side, spin-down will go to the other side. But in a ferromagnet, because there are more electron will spin up and less electron will spin down, so there will be a negative charge accumulator on this side and positive charge accumulator, and this explains polarity theory, the enormous Hall effect. Okay, now in early 70s, two Soviet scientists, Guang and they realized that now imagine this material is not magnetic, but ordinarily non-magnetic or semiconductor. You still have this spin-dependent scattering, but there's no transverse Hall voltage, but you have spin current. Spin up electron going this way, spin down going that way. And this is the first concept proposed by these two scientists. Is called spin Hall effect, which at that time you rely on impurity, so it's called extrinsic spin Hall effect. Of course, this was not followed up because at that time there's no such thing as spintronic. Okay, now until around 2000, many people start to rethink this spin Hall effect. One important paper published by Tokyo group and Stanford group is that they found that for even pure semiconductor without impurity, if it includes spin-orbit coupling, then this typical semiconductor can be derived by so-called Lagrange band structure model, and from that model, you will find that in addition to ordinary velocity, you have so-called enormous velocity. That gives rise to a spin-dependent transverse spin current, and that's, this paper actually will start this modern research on spin Hall effect. Okay, and quickly this was confirmed by the Astron group in Santa Barbara. You can see that beautifully. You see using optical measurement, you see the spin accumulation up on this side and spin down on that side. Okay. Now this has been causing attracting enormous interest in solid-state physics because application in spintronic. Now let me use slide why it's so interesting. Basically, to have spintronic, you need to generate spin current, detect spin current, and importantly to manipulate spin current. For example, if we want to make a spin transistor. Now, to generate or to detect spin current, you can use ferromagnetic metal. Okay, as read. For example, if you have this ferromagnetic metal Fermi level current will be semi polarized, or even better for hard metal. So, but spin Hall effect allow us to generate spin current without the magnetic material. That may contaminate current semiconductor industry because you don't want a magnetic field or magnetic material. So that's why it becomes so interesting ever since. Okay. Now, and also inverse spin Hall effect. I'm going to tell you what's inverse. Allow people to detect spin current. Okay. So that's make spin Hall effect so interesting. Now, since this theory talk and young people in the audience, so let me briefly introduce a nice formalism to calculate all intrinsic spin Hall effect, which when I learned solid state, I rely more or less on this classic textbook, S. and that will tell you that within semi-classical formalism, velocity of Bloch electron is actually gradient of band structure in the momentum space, and the momentum velocity, which actually is is force. Okay, can be written as gradient of potential in real space minus Lorentz force, which is magnetic field. Now, if you are a theoretical physicist, in that sense I'm not. Okay, you may feel uncomfortable with that. Okay, because they are not symmetric. But some people notice that. Okay, one of course is Chen Liu and his student, and realize that. Then they take Berry phase into consideration, and you realize if you take Berry phase into consideration, this term will appear. Okay, so this is called enormous velocity, which because this k dot is parallel to E, so this term will perpendicular to applied electric field, and this term gives rise to all the Hall effect. Okay, intrinsic Hall effect. Now, if we plug into semi-classical theory, you'll find that okay, this is now velocity for Bloch electron. You have two terms. One is the ordinary conductance or resistivity. The other is enormous Hall conductivity. Okay, and then this can be beautifully written in terms of Berry curvature, and then you get enormous Hall conductivity. Now, if you replace this, go back. This is the charge current operator. Okay, if you replace this current operator with a spin current operator, you get the spin Hall effect. If you replace this with the orbital angular momentum velocity, you've got orbital Hall conductivity. So within this formalism, you can calculate all the intrinsic Hall effect. Of course, all this, in most cases, you need a spin Hall decoupling. Okay, so I think I'm the first person to develop this into the MTO code, or into any ab initio code. So at that time, we saw Dirac equation and put this into the code. And this is the first result we have ever been presented by ab initio calculation. Okay, so this basically show you that in this typical semiconductor, we have a large spin Hall effect and so on. Okay. Now, let me move on to metal. Now, I told you that in the case of semiconductor, spin Hall conductivity is small, and also you need optical to measure spin Hall conductivity, which is of course inconvenient for spintronic application. You want something using electricity, not optical. Okay, so this of course idea was picked up by Ting Tang group in Harvard. Okay, they first proposed to use, and not proposed, actually realize using inverse spin Hall effect. I show you this is spin Hall effect. You inject spin current, spin up going this way, spin down going that way. But if you inject, sorry, this is charge current. Okay, ordinary charge current. Okay, if you inject now pure spin current, okay, spin up electron going this way, spin down electron also going this way. Then this will be next to charge here. And that means because charge neutrality, there must be positive charge here. You have a measurable charge voltage, Hall voltage. Okay, so this is called inverse spin Hall effect. And they use this to measure spin Hall effect of aluminum. Okay, and they found spin Hall conductivity, which is in order 27. cm. Okay, and this idea was picked up by many groups in Japan. Okay, in particular, this Tokyo group, Professor Otani in ISSP, and they, for the first time, they measured spin Hall effect at room temperature, which is very exciting because in the semiconductor is at very low temperature. Okay, and then also spin Hall conductivity is huge, 240. Okay, now so and then in order to have application, of course, we need to understand the mechanism and also to be able to have a feeling which material to discover large spin Hall effect. Okay, so that's the point that we come in. Okay, for example, platinum measured by this group, the band structure is very complicated. You cannot use model like Latinger model or Rashba model. You actually need to do material specific first principle configuration. Okay, so that's why we come in. Okay, so first I apply my code to do FCC aluminum and found that the same order of magnitude and at a very low temperature, same order of magnitude as tin can measure. Okay, and then we also apply to platinum. Okay, now this is important finding because we found that platinum has a huge spin Hall effect, 10 times larger than experimental people measure. Okay, so you can see that this is the spin Hall conductivity calculated as a function of Fermi level, and for platinum we are lucky because in the real Fermi level we have this peak here. Okay, which is I'm going to explain. Okay, and so now, yeah, Tao just ask for any reason. The reason is that I plot. You can see I plot spin-orbit coupling band structure without spin-orbit coupling band structure. The red one is without spin-orbit coupling. You can see that they are doubly degenerate at this L point near the Fermi level, and also at the X point near the Fermi level. When you include spin-orbit coupling, this because platinum is very heavy, spin-orbit coupling splitting is in the order of 1 eV. Okay, so the huge spin-orbit coupling can open. The Fermi level is falling within this gap, and that's important. Now we try to understand that by calculating spin barrier curvature band by band across the Fermi level. Okay, so that's what we got. First band barrier curvature and spin barrier curvature, and second band. You can see that there's peak appear here, all very flat. Suddenly there's peak, and this peak are impaired. Okay, one negative, one positive. Okay, and this actually occurring here. Now imagine that if this both bands are filled, they cancel each other. Now if we look at this band, and coming back into this picture, you can see that this occurred at a low point. One band 4 has a negative peak, band 5 has a positive peak. But here is important because this is occupied, this is unoccupied. So then this makes huge contribution to the spin Hall conductivity. The same happening here in the X point. You can see that there's one occupied, the other unoccupied. So from this you can see that because Fermi level falling in this spin orbit coupling gap, and then we have a very large contribution from occupied band. So that's now, as I mentioned before, experimental people first measured 240, and we have tough time getting paper published because pretty much higher. Okay, but fortunately, eventually we get the paper published, and this experiment people cool it down and found that at the 10 Kelvin it increased to 1,700, and then a lot of people measured, more or less confirmed that we got the 4,000, and this about well, this for me that's very good. Same order magnitude. Okay, now there's the consensus that the platinum has the largest spin Hall conductivity among the transition metals. Okay, now because of this, it has been used in spin current generator and detector in many important spin transport experiments. For example, spin seebeck effect using platinum to measure the spin seebeck effect, also using platinum to switch the magnetic domain to have NRAD application. Okay. Another one is to used to inject spin current because it can generate large spin Hall effect can generate spin current. Okay. Now the story is not ending. Okay. So we also calculate for a number of materials, for example gold, and we predict that will be smaller than platinum, and this is the experimental measurement, and they are in quite a good agreement. But then soon there's a paper coming from Tofuku University Sendai in Japan, and they reported that in gold ore bar they discovered really gigantic spin Hall angle, which is 0.1. If you transform that into spin Hall conductivity, it's 42,000, 10 times larger than I predict for platinum. Okay. Now then the question is, what could be the spin Hall effect? Okay. Now if we, I did the experiment before. Okay. Now they're using a sputtering. Okay. Now when you sputter, if I'm wrong, experiment people please. So when you sputter to make a sample, of course you many guns, and so I think that when you make this ore bar, this iron, platinum, and some other impurity will go into this gold ore bar. Okay. So then what I think is that we should study defect-induced spin Hall conductivity. Okay. And then I performed band structure configuration for pure gold, gold with a gold vacancy, and gold doped with platinum, and gold doped with iron. Okay, you can see that if you dope gold with vacancy, not much change. If you dope with platinum, we have this prominent peak due to impurity, but which to me is 1.5 eV below the Fermi level, which may not affect transport very much. But important one is that if we dope with iron, and you can see that there's a huge peak appear at the Fermi level. Then you do spin polarized calculation, and spin up electron will split and well below the valence band, and then spin up band will split into T2G and E2 band. And T2G band is right at the Fermi level, and in this case you can model that using angular momentum equal to 1, or p orbital. And then if you further include spin orbit coupling, you split into nz equal to -1, 0, and +1. And then this gives rise to a large orbital magnetic moment. And now my collaborator, Professor Nakaosa, is expert on Kondo effect, and then we immediately thought that this could be multi-orbital Kondo effect in this. And then, of course, let me just quickly explain to you a Kondo effect. Some of you may not know it. This basically, in 1930s, a Dutch physicist called De Haas, he found that in some metal, if you dope with a magnetic impurity, normally when we measure resistivity as a function of temperature, if you cool a sample down, the resistivity go more or less linearly. But for dilute magnetic impurity metal, you will find that at a certain low temperature, the resistivity not become flat, but goes up again. Okay, and this was a puzzle for a couple of decades. Then Japanese physicist Jin Kondo came in, and then he started this by using nowadays known as Kondo model. You have free electron, and then impurity magnetic moment coupled with conduction electron, and then he solved problem using second order perturbation, and then he found that in addition to this linear term, you have this Kondo contribution, which at a certain low temperature it becomes singular and the resistance go up again. And this explains this effect discovered by De Haas, and now it's known as Kondo effect. Okay. Now, if you do STM measurement, Kondo effect basically at the low temperature you will see this Kondo resonant peak. This is the graphene we calculate. Okay, gigantic one. This you cannot miss it. Now this gives rise to a large resistivity. Now, of course, then we do some very hand-wave calculation based on quantum mechanics textbook to find out what quantity is related to spin Hall angle in this case. Okay. Eventually, we end up with a spin Hall angle expression like that. Okay. And later on, we further simplify it, and you can write spin Hall angle as the partial wave scattering phase shift. Okay, so this is P phase shift, and this D is angular momentum equal to 2. And then if you have this phase shift, and then you can estimate spin Hall angle. So now, how to estimate phase shift? Now, you some of you may know that there's a sun rule called Friedle's sun rule, okay, which relate partial wave phase shift to orbital occupation number. Okay. Now, doing a initial calculation, you can calculate orbital occupation number. Then we put this in, we estimate spin Hall angle 0.1. Okay. I should not take this, very happy about that. I'm happy about its same order magnitude. Okay. Now, so this was some kind of very interesting, and the editor asked this Kondo expert, Pierre Coleman, and some of you may know him very well. He was here in Taiwan last year. Okay, anyway, he's TKD's friend. So he wrote a comment saying that now if I'm right, or if we are right, observation of giant spin Hall effect result from Kondo effect, we add new twist to this story. Okay. Now another thing is that he said that this fascinating state of affair, possible synergy between speed application and condensed matter physics could be very exciting and unexpected. Okay. Now, and I'm also happy that the same group, Sendai group, originally they unintended discovered this gigantic Hall effect, but after our paper, they deliberately go. Okay, and then found that this Hall angle remained the same for very low concentration. So this proves that the skew scattering mechanism we predict is correct, at least qualitatively. Okay, so that's the spin Hall angle and how we relate to a classical problem in condensed matter physics, which is quasi-orbital Kondo effect. Now that's let me coming back to the final topic. Basically, this is a very hot topic nowadays, and Steve already mentioned something to do with topological material. Now, let me refresh ordinary Hall effect again. As I told you before, Hall resistance is linearly proportional to applied magnetic field, but that's people know before 1980s. Okay, you know that in 1980s. Von Grising and co-work discovered that if you further increase magnetic field, okay, and this Ohm's law, well, not Ohm's law, sorry, this linear dependent will check. Okay, you can see that the plateau started to appear. Okay, and further on, furthermore, they discovered that this plateau can be related to an integer inverse. Okay, now, and this we know is quantized. Quantum Hall effect. In the meantime, they discovered that this longitudinal resistivity becomes 0. Okay, you might ask, is this superconductivity? In fact, it's not. If you write resistivity as this kind of two-dimensional tensor, you take an inverse, you get the ordinary conductivity, and you find that conductivity is also 0. So this means that in the plateau area, ordinary conductivity is actually 0, means this is insulating phase. Okay. Now this quantization is very precise, and so now then the question is, what causing this such intriguing phenomenon? Okay. Of course, this insulating phase can be explained by lambda level formation. You know that when you apply very strong magnetic field, Lorentz force make electron in the physical picture make it circulating and will not move conducting electron. But in the quantum mechanics level, you solve this equation and you find this continuous level now become quantized, and this is known as lambda level. When in this plateau area, Fermi level will be within this gap, and then you have integrated phase. But that's not terribly interesting. More interesting is that 2 years later, David Thoras and his colleague discovered that this quantized Hall conductivity can actually be written in terms of Barry curvature, integrate over a two-dimensional Breuil zone. Okay, and this number is called TNKK or Chern number. Okay, so and this kind of thing is called Chern Insulator. Okay, now you can see that from topology point of view, any two-dimensional sheet can be wrapped up into a donut. Okay, and then you have Barry curvature on the surface of this donut, and then according to topology, and this can be quantized either 0 or 1. Okay, so and that this group relate for the first time relate this quantized conductance to topology and Chern number. Okay, so in that sense, this quantum Hall effect is the first topological phase people discovered, not the current topological material. Okay, now the question is, you have an insulator, but it's conducting as well. So this conflict, how can you resolve that? Okay, now as a physicist, you know that this kind of ideal two-dimensional does not exist when you want to do measurement. So then, if you want to do measurement, you have to make a sample. When you make a sample, you create edges. Okay, now in the real space picture, when you create an edge, lambda level will bend at the edge, and then although bulk is insulating and this edge is become conducting. Okay, but then its more beautiful argument is based on now popular argument. It's called bulk edge correspondence theorem. Basically, this two-dimensional electron gas under strong magnetic field is in is a topological phase. Okay, but on the other side of the edge is a vacuum, which is topological trivial. But this theorem tells you that when you have two topological different materials put it together, you have interface. And now to go from one topological material and to another, the gap must close. If gap must close, you create an edge step, which is metallic and also one-way propagation. So let's explain why we have a bulk insulating phase conducting on the edge. But if you still don't believe, if I will do is that you express perform calculation. Okay, like in particular we're doing first principle or tight binding calculation. This is actually done by Hasuka in Japan, and they found that in addition to this bulk lambda level, you have this edge state, which is protected by topology. Okay, and this, but because this number of edge state is integer, and then you have integer quantum Hall effect. Okay, now so by now I convinced you that the integer quantum Hall effect is an intriguing phenomenon which has what do you call dissipation is edge current. Okay, and now the question is, this kind of experiment you need a very low temperature and also very strong magnetic field. For application point of view, can you find this integer quantum Hall effect at a high temperature without magnetic field? Okay, of course, this smart people like Duncan Horden already see that. Okay, he proposed in 1988. This is all this Duncan's paper and David Thoras paper. You know, this is Nobel Prize winner, winning paper. He already proposed before graphene actually discovered. He proposed in this graphene lattice, he added this assume that there are magnetic flux in this A side, B side, and has opposite side, and the electron hopping around this A side, B side is equivalent to spin-off coupling. Okay, and then he saw this Hamiltonian and get to the phase, and he found that within this parameter regime, and this the system it becomes topological non-trivial. Okay. Now this flux can be realized in kind of exchange interaction in a ferromagnetic material. Okay, without the applied magnetic field. So this can be called quantum Hall effect without lambda level or without magnetic field. Of course, this is too ideal and difficult to realize. And you know that after topological insulator was discovered, these people, a group of people led by Guang in Institute of Physics in Beijing, they realized that to have real quantum anomalous Hall phase, you needed to go magnetic impurity into this what you call topological insulator. Professor Guang already mentioned. But anyway, they performed first principle calculation and found that if you dope this material, you find that chromium dope is actually an insulator, magnetic topological insulator. And they calculate Hall conductivity. You realize that 1 quintet layer, 2 quintet layer, and 3 quintet layer, they all have, if you increase the exchange interaction, they all have a quantum transition from 0 to this Hall conductivity. Okay, and you know this now. This becomes famous. Then, I mean, Zhonghuang and the Xie Xiguan are collaborating. The Xie Xiguan group spent 3 years designing this sample. Eventually, they confirmed the prediction that they see quantum anomalous Hall phase. Okay. Now, then, why I say all this? Everybody knows this, is it? Now, of course, this guy got this first Chinese future science prize. But that's not my main point. My main point is, what can we do? Okay. Although now they discovered this at the 30 millikelvin, which is very low. Okay. And now, why is that? People speculate, including myself, because the band gap is tiny, 10 millielectron volt, weak exchange interaction because it relies on dialectical magnetics. And another thing is low mobility because maybe you introduce magnetic impurity, you also increase resistivity. Okay. So then we started to think, can we find a material with a large band gap? Hopefully, will have a high temperature quantum anomalous Hall phase. Okay. Now then first thing I return to oxide. I showed you the oxide at the beginning. Okay. We're coming back to oxide because oxide has a high temperature superconductor, colossal magnetization resistant, calm metallic, all these interesting properties. Okay. And but all these are 3D transition metal. Okay. Now 3D transition metal, you have strong correlation, which often lead to topologically trivial multi-insulator. Okay. But some people may not agree. But leave that aside. And so we look for quantum anomalous Hall phase or quantum Hall effect without magnetic field in 4D and 5D. Now the reason I written down here because 4D and 5D has stronger spin-orbit coupling and orbitals are more extended. Hopefully we don't need many body theory to deal with it. Okay. So now we look at quite a few systems. In the following, I just want to show you one system we look at, which is layered oxide, potassium rhodium dioxide. Okay. Now this actually people probably familiar with because some 10 years ago people was interested in cobalt dioxide, which is a strong correlation, superconductivity, thermoelectric, and many interesting properties. Now, what do? We look for element underneath cobalt. Okay, the same structure as cobalt, but we now have 4D, and then we study all possible magnetic configuration up to 2 by 2. Now we found this magnetic structure are stable. Okay, and then we calculate all the total energy. We found that this configuration actually non-coplanar 3 into the center, 1 going down. This the total spin moment are 0, but this has lowest energy. You can see this is in millielectron volt. Okay. Now all these configurations are metal. Okay. 1 minute. Almost 1 minute. Okay, then we have gap 0.2. This is gigantic gap. Okay, and then we of course to understand that we calculate J1 first near neighbor exchange and second near neighbor exchange, and according to classical quantum Monte Carlo and classical Monte Carlo simulation, we found that this J over J2 is within this non-collinear magnetic regime of this expression. Now the question is, we found a magnetic insulator. What's the nature of gap? Okay. Now we again perform this enormous Hall conductivity calculation. We were delighted to find that this actually conductivity is not zero but quantized to 2. Okay, Chern number equal to 2. Then this is a Chern insulator. Okay, and this is so-called enormous or 4-phase. But why this is so special? I mean, nowadays if you find such a phase, you cannot publish it in physical letter because so many systems have been found. Okay, now it's special because normally this kind of phase is due to large net magnetization and spin orbit coupling. So far, we did not include spin orbit coupling. So the question is where this quantum enormous Hall phase comes from. Okay, now this reminds us that a long time ago, Tokula and Nagaosa published a paper proposed that without spin orbit coupling, but if you have magnetic structure which are non-coplanar, okay, then this magnetic moment, if we put it together, will generate a magnetic flux. Now, when electrons hop around this magnetic flux, you will also feel a magnetic field, which gives rise to enormous Hall effect. But because this is due to topological spin structure, so it's called topological Hall effect. But what they report here is only 1 or 2% of quantum conductance. But what we discover is quantized, 100% of quantum. Well, it's quantized Hall conductivity. So we can actually explain this using cartoon picture. We have 4 moments per unit cell. If you put it together, you will generate a solid sphere. Solid sphere has 4 pi, you divide by 2, you've got the belly phase, we will generate 1 Chern number, but we have 2 layers, so we've got 2 Chern number. But to be, okay. We also calculate edge state, but now since Chern has standing up, so let me summarize. Okay? Basically, my message is that quantum mechanics-based first principle calculation has become a powerful tool in condensed matter and material physical research. Okay. Now, they prove crucial to understand some of the sophisticated phenomena observed occurred in condensed matter system, and also enable us to uncover or even predict new material with exotic property, and allow us sometimes to design functional material with technological application. Okay. Furthermore, analytical solvable quantum problems are quite limited. Okay. On the other hand, new computing paradigms such as quantum computing are emerging on the horizon. Okay. So, thus in the future, first principle calculation will play an even more increasing role in condensed matter and material research. Okay, I need to thank all my collaborators here, and also thank funding agency, Ministry of Science and Technology, Academic Center for Theoretical Science, also my colleagues, the Kender Foundation. Okay, thank you for your attention.
Everybody work on this.
Yeah, as usual, Sanka already grew material, but which one is very good metal. So we asked him what's the chemical composition, but he cannot identify.
How sensitive is the final result related to purity?
Oh, of course, if you dope, you make it metal, and then it's not semiconductor anymore, so you basically destroy the quantum economic form. Yeah, because if you dope or it's not a stoichiometry. The Fermi level will not be really discussed, and then it might move up or move down. At the moment, Shankar's sample, I think it's somewhere here, is highly conductive. And
because the rotation level is right.
first, I asked him to check composition, but he cannot tell what's the composition of potassium. Well, he's in your institute now.
But he did make the crystal structure.
Yeah, you make it a crystal structure in a set. Yeah, but as I said, you need the stoichiometry is important, like cobalt dioxide, sodium content determine superconducting, magnetic, or thermoelectric. So, yeah, you can tune.
You need cobalt dioxide, you need water.
But he got many customers, so it's difficult to ask him to concentrate and tune one system. Yeah.
Yeah, in your earlier work on the spin Hall effect, you did calculations for the platinum case.
Yeah.
To my knowledge, even up till now, experimentally, the spin Hall angle for platinums can still vary by order of magnitude from group to group.
You have a very good question, but
so could you shed some light
the answer
on it?
is simple. Because spin Hall angle equal to spin Hall conductivity divided by longitudinal conductivity. Longitudinal conductivity is very sensitive to sample condition. Yeah. So what do we calculate? We can say that if you convert to spin Hall conductivity, that should be more or less stable. But talking about spin Hall angle, you know, it's two quantity. It's not one quantity.
But in that case, if one make a material standard, like for example, that you have iron purity in gold,
Yeah.
then one should be able to make a uniform iron purity in a gold film. So in that case, sample to sample should be the conductivity should remain the same.
Yeah, but I don't know how experimental QPL can make a very uniform sample, you know, with the ion impurity and things like that.
So you have impurity value
No, I think Professor Hong asking this ion dope gold problem.
It should be even MBE should be able to control very
Yeah, then, well, I don't know the answer because that's a question to you, isn't it? Maybe you can make a uniform sample. But basically, to say, we calculate this is in principle quite a robust intrinsic spin Hall conductivity for platinum. But that quantity, I can say, is quite reliable. But spin Hall angle is different because you divide this quantity by something else. That quantity is not controllable when you make sample.
other number.
Oh, there's a paper by Alexei Hoffman in IEEE Nature Transaction. He summarized at that time, 2015, all the measurements. Yeah, as Professor Ko said, it ranged from varies a lot from say 200 up to a few thousand.
Other quantities which can be measured or determined, but also here zero other than
Well, there are many quantities can be measured.
yeah. So
But
maybe later it depends on the.
no, to me, spin Hall conductivity should be consistent because its quantity stand alone. But spin Hall angle is a compound quantity. It's like when we're talking about physical unit, you have fundamental quantity and then you have a compressed, a compound quantity, like magnetic field. And here is fundamental. It's Newton divided by n squared or something. That's what I mean.
Well, I mean, platinum has been used quite openly in this conducting material for a long time. So, is this, would that be, I mean, you said that it's such a high
Yeah, so that's why, as I said, being used in many spin transport experiments in the past decade. In particular, it's the Japanese group in Sendai. They always the first to publish spins, seabag, many experiments. And they always use platinum. Oh, your friend Charlie Chen also used it. Also Professor Course.
Okay, so let's thank our speaker for Mr.
I mean, delay for lunch.
We have 10 minutes today, so just start on